Professor Yoshihiro Ito from University of Kyoto. He is coming here today not as only a specialist in this field, but also as an ambassador for his university. So please take this opportunity seriously into account and take advantage of it. And if you want to talk with him, let's talk with him. It doesn't matter if you're a volcanologist, a geologist, a geochemist. It doesn't matter. He's a phenomenologist, a very good one. But he'll take into account all your comments. And he's really interested in knowing you as a community, knowing us as a community. So now Esmeralda will introduce Professor Ito-san. Ito Sensei. Okay. So Esmeralda, please.
Bueno, gracias por estar aquí. Les doy la bienvenida a este seminario institucional extraordinario organizado en el marco de la visita del profesor Ito Yoshihiro de la Universidad de Kyoto, Japón, quien, como menciona la doctora Marina, estará en el instituto del 19 al 22 de noviembre. También, como ha mencionado la doctora en sus correos, esta visita forma parte del proceso de internacionalización que está promoviendo la UNAM a través de su Plan de Desarrollo Institucional 2023-2027. Como parte de las actividades programadas de la visita, el doctor Ito ofrecerá la presentación del día de hoy. Entonces voy a comenzar por presentar al doctor Ito, después el doctor va a exponer y concluiremos con una sesión de preguntas y respuestas moderada por la doctora Marina. Y bueno, el doctor Yoshihiro Ito es profesor asociado en el Disaster Prevention Research Institute de la Universidad de Kyoto, donde forma parte del Research Center for Earthquake Hazards. Su trayectoria académica y profesional lo posiciona como un referente en el estudio de terremotos y desastres naturales. El doctor Ito completó su formación en la Universidad de Utsunomiya, Japón, donde obtuvo su grado universitario y de maestría en la Facultad y Escuela de Graduados en Educación. Posteriormente, obtuvo su doctorado en la Universidad de Tohoku, Japón, especializándose en ciencias de la Tierra. A lo largo de su carrera ha ocupado posiciones relevantes, incluyendo investigador asociado en la Universidad de Tohoku, técnico y becario de investigación en el National Research Institute for Earth Science and Disaster Prevention en Japón y profesor asistente en la misma Universidad de Tohoku. Desde 2013 es profesor asociado en la Universidad de Kyoto. Sus investigaciones han sido respaldadas por importantes financiamientos, incluyendo del Japan Society for the Promotion of Science y otros programas internacionales. Entre sus proyectos más destacados se encuentra el estudio comparativo de terremotos lentos entre Japón y México y la evaluación de riesgo de grandes terremotos y tsunamis en la costa del Pacífico mexicano. El doctor Ito ha contribuido significativamente a la literatura científica con publicaciones recientes en revistas de alto impacto, incluyendo las revistas Seismological Research Letters, Technophysics y Geophysical Research Letters y también la revista Science. Además, ha liderado proyectos innovadores en áreas como la viscoelasticidad de materiales geológicos y la caracterización de estructuras sísmicas complejas. Comprometido con la educación, el doctor participa en programas que combinan observación oceanográfica y enfoques culturales para la educación en materia de desastres naturales. Hoy nos presenta la ponencia titulada Enhancing Earthquake and Tsunami Preparedness for Mexico Outcomes of a 6-Year Japan-Mexico Project Annex, en la que compartirán sus avances y perspectivas del trabajo. Adelante.
Muchas gracias. Muchas gracias. So, no puedo hablar español. So I'll change to the English. Sorry. So thanks so much for the very kind introduction of mine. So tonight I'd like to talk about my last project result, which was done as a international collaborative research between Japan and Mexico. And we also have in the next stage means we also have the other international collaborative research between Japan and Mexico. And I'd like to explain briefly what we need to do then the next. So now here I'm showing the tsunami intuition or tsunami height observed after the 2011 Tohoku earthquake. When Tohoku earthquake occurred, I was in the Tohoku University. as a seismologist, and we deployed the ocean bottom instrument offshore, just above the main shock area of this earthquake. Of course, we got some very important data from the earthquake, but I didn't do anything to prevent or to rescue to protect their life living in the coastline, even if we had the data. So this was my motivation to have the new international collaborative research in Mexico. As you know, in the Mexico has also have this almost same technique setting with Japan. The Cocos Plate is now subducting beneath the North American plate. Owing to this subduction system, you also have a very big risk of the future large earthquake. Actually, in the past, you also have the large earthquake in 1933 in Jalisco. At that time, you also have the large tsunami damage in Cuyotoran. So, and if you look at the Mexican coastline, as you know, we have the two very famous gaps worldwide. One is Guerrero seismic gap, which are located almost center of these figures. The other one, Tehuantepec gap. During our project, we have the large earthquake in Tehuantepec that was not an interplate earthquake, but still remained the Tehuantepec gap as a seismic gap on the plate interface. And we also have the other seismic gap in the Guerrero. Last project we were focusing on the research to our understanding about what actually happened in the Guerrero seismic gap in this area. If we roughly expect or estimate the largest magnitude in this area, if almost all a gap or rupture as an earthquake, that is a maximum magnitude almost close to magnitude 8. If you have if we have the magnitude 8 plus earthquake in the Guerrero seismic gap, we need to consider what actually happened along the coastline, especially not only from the strong motion, but also from the tsunami induction model. We need to consider what we need to suggest to the people living in there. So to achieve this idea, we did the international collaborative research from since 2016. So we used the research budget from Japan. We call it as a SATREPS. So this, as you know, the SATREPS is one of the very important budget for scientists in Japan. But this is the strong point of this budget is not only focusing on science result. Because if we try to use the SATREPS, we need to achieve some of the result related to the people saving some of disaster or some of the worldwide issue. Especially if we look at focusing on the disaster case, we need to provide an idea about how to mitigate the disaster, especially in the tsunami or earthquake. This means that if we try to use this budget, the goal of this project is not understand the earthquake or tsunami physics. We also need to provide the idea to mitigate the disaster of tsunami and earthquake. Okay, so now I'm trying to show the movie to explain what we actually did. So this movie was made during the first cruise of Guerrero. This is requested from the Japanese embassy in Mexico because they try to use my video as a kind of promotion of their work. After arriving in Mexico, I went to the supermarket or no shopping mall, and I got the video camera, and I did everything during my cruise. But yeah, this is maybe 3 minutes or something.
The Pacific coast of Mexico is an area with a high risk of disaster related to megathrust earthquakes and tsunamis in the near future. In particular, a future megathrust earthquake and tsunami are expected in the Guerrero seismic gap. Therefore, social implementation and federal researches into disaster mitigation are urgently needed. This project is aimed at providing earthquake and tsunami scenarios based on the latest observation data and computational methods. Develops earthquake and tsunami hazard maps and tsunami evacuation guidelines for the mitigation of damage caused by the future megathrust earthquakes in the Pacific coast of Mexico. We, international collaborative party between Japan and Mexico, tried to construct the first sea-bottom seismic and geodetic network just above the Guerrero seismic gap, 7 ocean bottom pressure gauges, and 7 ocean bottom seismometers, and 2 GPS acoustic geodetic sites will be deployed off the Guerrero state. By using these we try to observe vertical crustal movement caused by interseismic plate motion, large and small earthquakes, and slow slip events, which is watched with interest by the rest of the world. Before starting the cruise, our ocean bottom instruments have been prepared in one of laboratories in the Institute of Oceanological and Limnological Science of America. They have been shipped to Mexico and finally assembled here prepared for the sailing of El Tuna.
Yes, this is a movie to introduce what I did. Especially today, Marina asked me how do we deploy the ocean bottom instrument? So I add this movie to explain what I did. Okay, so now I'm showing the project design, which we done in the last project. So now we have the three groups. First group is focusing on the monitoring of seismic and geodetic deformation offshore and onshore of Guerrero, which deploying the ocean bottom seismometers and ocean bottom pressure recorders, which is to measure the vertical crust movement. And we also deploy the GNS side and onshore, as well as broadband seismometers. And based on this observation, especially focusing on the activity of slow earthquake around the Guerrero state, we tried to make made a model, strong motion and the tsunami model, which I expected from the strong coupling area offshore Guerrero. After based on this computing technique, we estimate the strong motion and tsunami intuition model in Shiwataneho especially. I will show the intuition model later. And we propose what they need to do to evacuate from tsunami. And we also provide a tsunami evacuation drill program, especially in the elementary school level. So almost all of group are tackled toward to the mitigation of the tsunami and strong motion from the future possible large earthquake of Guerrero. So if we simplify that project, we did the monitoring and made the modeling and achieved the assessment of outreach. This project design not so new idea. Almost all Japanese tsunami mitigation program or the other mitigation program in the world will doing like this. But one of strong point was in this project was we did this project within a relatively small group. This means we communicate well between the monitoring group and the modeling group and assessment and outreach group. So finally, we achieved the good product from this project, and successfully we got the high level of evaluation from Japanese government after finishing this project. So on this project, from Japanese side, basically Kyoto University joined this project, and as well as the University of Tokyo and Kobe University. Maybe Kobe University, one of professor working in the Kobe University frequently visit here, Professor Yoshioka. Here's one of my good friend working in the international collaborative research. And the Mexican side, basically UNAM in the Mexican campus, especially Institute of Geophysics, joined this project. And for outreach and the assessment part, Senapure also joined this project. So after starting this project, so our idea was shown in the science magazine as a kind of the news, what we need to do, what we are doing in the of Guerrero. That it's not starting just at that time. Our project was not started yet, but kind of the reporter in the science magazine very interested in our project, so we try to introduce what we need to do the next project. So, and finally, 73 researchers and 27 students in Mexico and Japan joined this project. In total, 11 academic and federal institutes are joined this project. And we used $6.9 million budget in total, a very huge budget. We did everything within the 6 years. So next several slides, I try to explain what we did. So I already explained this part in the video. I established our ocean bottom temporal observation network offshore Guerrero with using El Puma. We deployed seismometer, ocean bottom seismometers and pressure recorders, and the GNSS acoustic transponder, which measure the horizontal, mainly horizontal displacement at the bottom as geodetical technique. So this is a map showing our station distribution. Left hand side showing the seismic network. Offshore, we deploy the seismometers showing by triangle of pink triangles. And we also deployed some of the broadband seismometer on shore as well. And right-hand side figures showing the geodetic network established during this project. We deployed ocean bottom pressure recorders to measure the vertical displacement, subsidence or uplift at the sea bottom. And we also deployed the GNSS acoustic technique, which combined with satellite technique and the acoustic sensing technique within the sea. So to measure the horizontal displacement, the station was shown by inverted triangle of yellow and the circle offshore. We also installed some of GNSS site onshore site. Of course, onshore site sensors still remain in this area. I guess almost data are accessible from all of the Mexican colleagues working in the UNAM, I believe. So with using the ocean bottom seismometers, we firstly detect the tremor distribution. Tremor is a tectonic tremor I'm saying about, showing by the red circle. Tectonic tremor is one of slow earthquake occurring in this area. So we say the slow earthquake, this is a relatively slow rupture process on the fault plane. The tremor, tectonic tremor is one of the smallest slow earthquake observed at this moment. So we observed tectonic tremor which near the trench, showing around here. These are mainly distributed near the trench, and we also realized the very low seismicity of Guerrero seismic gap. The microseismicity are shown by the black circles. If you look at the center of this map around here, there are almost no seismicity area. This is suggesting the two possibilities. One is a strongly coupled area and toward the future earthquake. The other idea, very loose coupling, very low coupling as a seismical. But our interpretation is that this area is very loose coupling or very low seismic because tectonic tremor occurring uplift portion of this area. This means that this area should be slipping, usually slipping or creeping, basically. And this is, if these are creeping or slipping frequently, this is not easy to understand strong coupled area. This is the reason why the center of this map, Guerrero seismic gap, is a loose coupled area. So if we believe this model, the chance of the larger earthquake of Guerrero is not so high, generally speaking. But if you look at the Tohoku case, we also observe the slow earthquake before the large earthquake, and slow slip area also slip again as a huge coseismic slip with huge coseismic slip. So this means that even if the chance of the large earthquake of Guerrero is low relatively, but we need to care about the huge earthquake of Guerrero still. So we call this area silent zone. This is named by the Raimundo Plata Martinez working in the Institute of Geophysics now. Okay. So we also analyze more the data from the ocean bottom seismometers. One of my students analyzed this data, and he also provide the much more tremors with using 2 years data. The Raimundo Plata Martinez only use 1 year data, and my student also reanalyzed the data again with using 2 years data. He detects the much more tremors showing by green circles, and still remain some of the silent zone remain in this area. Not this in this area still remain the low seismic coupling. Find out the small tremor activity, but no kind of the microseismicity. Microseismicity is one of the small fast earthquake. So recently we use the 2 words. Slow earthquake means like a slow rupture process. If we say fast earthquake, this is a kind of the original earthquake previously. Now we use a fast earthquake or slow earthquake. In this area, there are very low fast earthquake seismicity, and with small technical tremor of a small slow earthquakes area. We still say this is a kind of silent zone. Okay, during this project, we also did the other work related to the slow earthquake. With using the previous seismic network, so our colleagues already detect the calculate tremor distribution again, shown by right-hand side figures, and they also detect the BLFE signal. BLFE signal is a relatively larger signal from the tectonic tremor, but still this is one of the slow earthquake. They also detect the VLFE signal in the Guerrero state. And this project also focusing on the other future that we try to understand what's actually happening in this area on the plate coupling area. We need to make a model, especially thermal structure is very important. And one of my colleagues working in Kobe University, he calculated the thermal model of in Nankai area, as well as the Guerrero area. That is not shown here, but comparing the Nankai and the Guerrero, we can lead to the new idea what actually happened in this area. Now this project is still ongoing. Now we try to understand the what actually happened on the plate interface, especially related to fluid interaction based on the thermal model. So, and the last project, during the last project, we also have some of the large earthquake. One is the Tehuantepec earthquake, the other one is the Puebla earthquake. The other one is also the, I forget the name of the earthquake occurring here. But that was a kind of chain interaction earthquake sequence coupled with the first earthquake and slow earthquake. Because firstly, a slow earthquake triggered by the Tehuantepec earthquake, and the activated slow earthquake triggers statistically of the Tehuantepec earthquake, and the Tehuantepec earthquake also activate the slow earthquakes in this area, and this slow earthquake also trigger the large earthquake. This like a chain-like sequence firstly observed in the world, I believe. And Mexican core is also working on try to understand seismic structure based on with using ocean bottom seismometer in this area. This is a work done by Marco Caro. He has now did the seismic tomography to understand the seismic structure beneath the offshore Guerrero. So, and we also tackled the new kind of technique to understand the subsurface, very shallow subsurface structure based on H/V spectrum. This is collaborated with Professor Paco Sanchez-Sesmar in the working in the UNAM Institute of Engineering. So we applied the H/V technique to the ocean bottom seismometers. This is a relatively new technique to understand, to estimate the subsurface structure close to the sea bottom. And this is mainly focusing on the a natural science side. We also need to evaluate the seismic risk or what actually happened as our observed strong motion in this area. To achieve that, we try to estimate the this is like a movie, I guess. This is not working well. Anyway, we also did the seismic microzonation in Shiwataneho. So firstly, of course, we knew the largest city in Guerrero along the coastline is Acapulco. Firstly, we try to do the evaluation, seismic hazard and tsunami hazard in Guerrero, especially focusing on the Acapulco because the largest city along the coastline. Because this project was supported by JICA. JICA is a Japan International Cooperation Agency. So they didn't allow to go to Acapulco owing to the security reason last at least 5 years. So this is the reason why we firstly focusing on Shiwataneho. Shiwataneho relatively low security, high security level compared to the Acapulco. But so we did almost all outreach activity and the educational program in the Shiwataneho based on our understanding. This is one very important result from seismic microzonation with using the seismic amplification factor estimated from the soil condition. Based on this one, very high risk in the center of the historical area of Shiwataneho. And we also did the economical vulnerability in the Shiwataneho as well, showing by the right-hand side figures. And also, finally, we show the seismic risk microzonation in Shiwataneho as well. That was done actually by the David Nobel working in the UNAM. And we also compare with the computational technique to estimate a result from computational technique to estimate the strong motion showing by left-hand side. So during this project, as shown here, the left-hand side figure shown done by Carlos Villafuerte. He is also working in the UNAM, young professor working in this field. So almost all result is from the Japanese side and the Mexican side as well. So this was, we said, this is a real international collaborative research. Because before starting this project, Victor Manuel Cruz Atienza, he is a professor in the UNAM Institute of Geophysics. He said to me, please promise to do the real international collaborative research during this project. Because as based on his experiments in the past, if they accept international research from especially European side, they basically ask to deploy the instrument and do the maintenance, everything. But almost all data are gone to the Europe in their lab. And all first paper basically done by themselves, well, in the European side. This means this is, in my feeling, this is not real international collaborative research. International collaborative research do everything together. So I he said, please promise, do the real international collaborative research during this project. I said, yes, of course. Please do together. Please do the best together. So as you show like here, main result is provided from Mexican researchers. And some of them are working in the Kyoto University as a PhD candidate. And especially Raimundo Plata Martinez got a PhD from Kyoto University. And so this is the result of the real international collaborative research, the last project. So, okay, we also explained some of the results from tsunami risk evaluation. So, with focusing on the Shibataneho, we try to make the tsunami model. But at this moment, we have no evidence enough to explain the tsunami model or to make a tsunami model of Shibataneho. So this is the reason why we try to do the stochastical model or stochastical technique to estimate the tsunami induction model. So in this stochastical model, we try to make a lot of huge number of the tsunami source model with keeping the same moment magnitude expected of Guerrero. We made a lot of tsunami model in this area. So based on the this one, now I'm showing the one of tsunami induction model as a maximum case in Shibataneho. So left hand, please look at the left hand figures. My first tsunami is coming into the bay of the Guerrero, sorry, Shibataneho. You can see one of the Yoto Harbor in the west side. That is a Yoto Harbor. Yoto Harbor, please look at around the Yoto Harbor. This was a kind of very important role to consider the tsunami mitigation. So basically, the tsunami induction coming from coastline, but owing to the existence of the Yoto Harbor, west side, that is called the kind of tsunami induction from west side to the east. This is called a complex situation, how to mitigate or how to evacuate from this tsunami in this area. So I say again, this is the worst case. The minimum case is not so serious. Not so serious, of course. But of course, we need to say that what is a maximum case? What is a minimum case? We need to consider both of cases. So how to evacuate from that to the maximum case tsunami? We did the tsunami kind of evacuation simulation of showing like here. The blue dot indicates one person living in this area. We make a kind of the map showing the road by gray shade. This is showing the street or road. After the earthquake, they are trying to evacuate from the tsunami. And red one, I guess this is showing the tourist, not only people living stay here. They are trying to evacuate from tsunami like here. Can you see the blue dot moving to the somewhere? So someone is trying to evacuate to north because north is located toward to the hill of this area, and east side also some of the relatively high area, and west side also the other hill. But if they try to evacuate from this historical area or to this area to east, they need to pass through this bridge. This is, please have imagine, if you have the very large earthquake, a strong motion in this area, can you try to pass through this bridge? Maybe they're not so easy to decide to cross this bridge. So, frankly said, if we have no kind of the kind of plan how to evacuate tsunami, maybe 30 or 40% or 50% more people will be die owing to the largest, such kind of largest tsunami invasion. So to save the huge number of the people living here, we propose some of the idea how to evacuate from tsunami. One of the idea is to use a high talled building, like a resort hotel or some of hotel, more than 3 or 4 stories more. We propose, please use this building as a tsunami evacuation tower. But this is a case of the result of the simulation. If we use the some of building in this area as a tsunami evacuation tower, some of guys, the number killed by the tsunami will dramatically decrease, especially area over here. If some of tower use the tsunami evacuation tower, only 10 people are maybe killed, around 10 people killed. But if I didn't use don't use this tower as a tsunami evacuation towers, there's 50 or even more people will be killed by tsunami. This is the result from our simulation. So of course, how to use this building as a tsunami evacuation tower? The local government of Shiwataneho, we try to continue to negotiate to use that. But now Shiwataneho people are trying seriously consider to use the tsunami evacuation tower. Yeah, like this. And so based on our tsunami simulation, tsunami invaded from the west side to east, owing to the existence of Yoto Harbor, I said in the previous figures. So based on this understanding, the local government of Shiwataneho decided to establish tsunami evacuation sign in this area. In this tsunami evacuation sign indicates which direction is a feasible or possible direction to survive the tsunami. And this is direction right here. Please look at here. But this is indicating this way, not this way, because this way is sometimes then dangerous, owing to the tsunami deviation from Yoto Harbor like this. So this sign is like it's here, please tower to the east. Even if that is not so high, looks like not so high altitude, but to survive from this tsunami invasion in the maximum case, much better to evacuate to east, not to the north. Now, this was already established based on our result of the simulation. So based on this idea, we also did the tsunami evacuation drill based on our scientific knowledge. We did this kind of tsunami evacuation drill in the elementary school level and high school level, as well as a hotel, people working in the hotel or hospital as well in Shiwataneho. So, okay, based on this understanding or product from the last project in Mexico, we try to provide or expand our idea from Mexico to the Latin American community, because our project or tsunami evacuation drill or educational material are developed in the Spanish. It's available to, it's applicable to the other area in the Latin American community. From Mexico, we'd like to distribute our product to the Latin American community in the next 10 years. So the one of the next project toward to the distribution of our idea to Latin America, we got the new budget from Japanese government. This is the Satellite project, phase 2. In this project, we're focusing on not only to understand the tsunami and earthquake mitigation and risk, we also applied our idea to save the port, especially focusing in the Manzanillo. So as you know, the Manzanillo is one of very important port in Pacific side because this is not only for the Mexican, but also Japanese side as well, because many Japanese companies or factory exist in Mexico. We use the Manzanillo as an import and export our product in the world. So we need to show, we try to show their idea how to save their product or how to keep the chain product or chain supply chain of their product, not only for Japanese company but also Mexican company as well. During this project, we try to show this idea to the Mexican government. So one of the idea to achieve that, we submit our proposal to Kyoto University, and our idea was accepted to establish international research observatory in Mexico. This means that we already keep our space to continue our activity in Mexico. So with using this international laboratory, we'd like to continue our collaborative research with Mexican colleagues, not only Mexico City, but also in this Querétaro campus as well. Now in the Kyoto University has some of the international on-site laboratory shown by here. But in the Latin American community, our laboratory is the first case. And this is very important point. Our laboratory is established in the Mexico City. And we also prepare an on-site laboratory for Mexican colleagues. This is available to use if you are staying in Japan, if you hope to do the collaborative research in the Japanese colleagues, then please use this space. We already keep this space. At this moment, we have no limitation for the period that we can continue this. We can keep this laboratory or working space, collaborate with you in the Mexico City as well as in Kyoto. Please visit Kyoto to do the collaborative research in future. This is the name of the on-site laboratory, international on-site laboratory. The name is International Research Laboratory for Earthquake and Tsunami Risk Cognition and Reduction. This is a little bit complicated name, but we try to focusing on not only understand the tsunami and earthquake physics, but also we'd like to reach how to mitigate the tsunami and earthquake disaster in future. So the name is the on-site laboratory name we call ILET. Yeah, please use ILET to progress your work in future. Okay, that's all. Thanks so much.
Thank you so much for your present. We do have some questions for you. Okay, so please. Oh, thank you so much. So do you have questions? Actually, the tsunami issue is very important.
So are you planning to deploy more ocean bottom seismographs someplace else?
Yes. So next project in phase 2, SATREPS project, we deployed the 8 ocean bottom seismometers off Chiapas above the Tehuantepec Gap. And we also, this project, phase 2 is not only between Japan and Mexico, but also this is a 3 countries project, Japan, Mexico, and El Salvador. And we also have a plan to install the ocean bottom seismometers of El Salvador. The next one will be now Institute of Geophysics has 8 ocean bottom seismometers, which is a short period type. But in this project, we try to donate the 6 broadband ocean bottom seismometers. With using that, we also try to detect the tectonic tremor or slow earthquakes of tail and back to evaluate the seismic risk.
Yeah, we've been working with Eurosat and Gulf for over a decade now. It's very interesting your work, but I still have a doubt. What's the cause of this, how to say, mentioned that the slow coupling of the interface, that's why it's a gap. What is the reason of this slow coupling? Do you have any hypothesis that you can share with us?
Yes, mainly main reason is occurring of slow earthquake down deep and up deep portion of the low seismicity area. If we look at the down deep area near the coastline, we also frequently observe slow earthquakes by onshore GNSS data. If you look at the up deep portion close to the trench, we also have observed the tectonic tremor. That is a kind of small size of the slow earthquake. This area surrounded by the slow slip area. So if this area strong couple as a seismically, it's not so easy to move up deep and down deep portion, because especially the down deep portion or up deep portion has a behavior as a stress shadow owing to the strong couple area. This is the reason why we expect this area is a low coupling.
Thank you.
I'm wondering if that silent zone has to be a little bit more, besides what you say, with the properties of the different rock layers that they are there. I don't know if you are searching a little bit about that.
In the silent zone, right? Yes. Basically, your subducting material is basically same, but we expect the occurrence of slow earthquake is related subducting seamount. So if we have a subducting seamount, amount of the fluid should be changed owing to the total amount of the fluid contained in the subducting plate or kind of normal ocean crust. And also providing rate of the fluid also change, as well as the some of the micro fracture above the subducting seamount within the overriding plate. Some of the micro cracks should be increased owing to the topography of subducting seamount. That is also the other reason to cause a loose coupling and occurring on the small micro size, small tectonic tremor, which is a small size of slow earthquake.
So more locally mechanical properties than they are there.
Yeah, mechanically, yes. For the awakening, I guess.
In the study case of Zihuatanejo, when you talk about soil characterization, which data you're talking about more or less, or which kind of soil characterization? And a second question, sorry, I'm not specialist in seismology. What was the difference between earthquake, tremor, tectonic tremor and earthquake? What is the difference between these two concepts?
Okay. The first question you were asking how do we evaluate the soil condition for the seismic amplification in the Zihuatanejo? We did the HOV observation or observational microtremor of Zihuatanejo with using the seismometers. So we, as well as data of the geological data, we evaluate the seismic microzonation inside Zihuatanejo. Yes.
But you didn't make some kind of mechanical characterization?
Maybe only we didn't do in detail about their soil physics. Yeah, the next stage we need to do evaluate the seismic microzonation based on the soil mechanics. Especially the soil mechanics in the port area is very important, I guess, if we have a strong motion, harbor or port, the port in this area we seriously expect the liquefaction, right? Owing to the strong motion. In this case, we need to seriously consider the effect of the coupling of the soil mechanics and the damage of the owing to the strong motion. And the second one, what is the difference between the slow earthquake, tectonic tremor, and fast earthquake? So if we compare the almost same moment magnitude of the first earthquake and slow earthquake, especially moment magnitude of about 7, the first earthquake rupture usually continue several 10 seconds, right? So rupture duration. They're very short, several 10 seconds only. But if you look at the slow earthquake on the magnitude 7 class earthquake, this is continue almost 2 weeks or 3 weeks or more as a rupture, one rupture. Very slowly processed. And owing to the very slow rupture process, the seismic energy was not so strongly radiated from the source. So this means that even if you have the magnitude 7 class slow earthquake in the source, or even if we stay in just above the source area, we never feel anymore. We never feel the shaking anymore. Now, this is a rupture speed of the rupture is completely different. If we directly say the rupture speed on the fault on the first earthquake is 1 meter per second, but in the slow earthquake case, several micrometer per second or several tens nanometer per second, very slow.
Thank you for your presentation. I have a more like a technical curiosity. How do you fix and level the GPS in the bottom? And if you fix it, then it mimics the formation at the bottom. But if you don't fix it, how are you sure that this is related to the formation?
With using the GNS acoustic measurement technique onshore, right? Offshore, you are talking about. So
Yes, the offshore.
Yes, the technique is almost same as the technique with to estimate the hypocenter or epicenter in seismological technique. As you know, the position of the ship itself are fixed with the GNSS signal. And we also have several ocean bottom side transponder at the bottom. If we send a signal to the transponder, they immediately reply the acoustic signal propagating in the sea. We measure the kind of the travel time of the ship to the bottom transponder. And if we have the sum of this transponder at the bottom, we can estimate the center of this array, bottom array. Based on the almost same idea of the estimation of the hypocenter or epicenter as a seismological technique. So
you measure the strain on the boat.
Yeah.
Basically.
Basically combined with the satellite and acoustic technique.
Thank you, Mariano. Other questions? Do you have other questions?
I have a very basic question, but it's a live question. Why are there no so many tsunamis in the Pacific coast of Mexico compared to the tsunamis in the other coast of the Pacific, no? Like Japan, like the Philippines and all of that. And what's the probability of having such a great tsunami as the one you show in your model?
Maximum case is close almost the top 5% or something, or top 10%. That's like close to the worst case. The other one is almost half in duration of the maximum estimation. But less than happiest case is basically almost no tsunami in duration. So if we mean tsunami modeler have enough information to estimate the past duration of the tsunami, we can directly estimate the possible tsunami source. But in this area, we have not so much data enough to evaluate the past tsunami duration or past huge tsunami. So this is the reason why we decide to apply the stochastic model to make the huge model. But this technique is also applicable for not only Mexico, but also the other area. There are no enough data about the tsunami induction. But of course, sometimes we also did take the same strategy to estimate the tsunami induction, because if the tsunami deposit itself is not so easy evaluate to compare to this is the last tsunami or last huge tsunami induction or storm sometimes. And if we try to ask the historical data possible, but that is also including some of the large ambiguity of tsunami induction. Because even, as you know, in Japan is one of the best area to do the kind of paleoseismology, because some historical data are remain. But even if in Japan, we can use some of historical document, it's not so easy to estimate the tsunami induction path. So in this case, we take the strategy to do the stochastical technique to make a model.
Yeah, I have a comment about your first question. So why Mexico has so few tsunamis? This is because Mexico is one of the fewest countries that you have the smallest distance between the trench and the coast. It's around 60 kilometers. If you go in Japan, it's maybe 200 kilometers. So when there is a thrust earthquake, most of the energy, part of this energy is released onshore, not below the water. So this is one of the reasons. So there are tsunamis, but not so often, not so big. So this is a good news. The bad news that we do not expect. So, and another question for you is that you mentioned following the standard comment about the seamount, and you mentioned the bulge of the forest just above the seamount, and you mentioned some kind of fracturing, things like that. I remember that you measured some heat flow data. Did you capture any anomalies in heat flow measurements above this bulge of that corresponds to the seamount?
No, at this moment we have no enough thermal data, because as you know, the El Puma has no dynamic positioning system.
Yeah.
If we try to measure thermal data from the ship, we usually deploy the kind of very big thermometers to the bottom, penetrated into the bottom.
Yeah.
After that, we need to keep the ship position at least 10 minutes or a little more.
Fixed.
Yes. So that is the generally speaking, the Japanese vessel has a dynamic position system to keep the position. But in the El Puma, there are no such kind of the one. So this is the reason why we give up to measure to get the thermal data. But actually, Institute of Geophysics has some of the ocean bottom thermometers, which is attached to the piston coiling system.
Yeah.
That is also possible to do if we have the other idea to measure the thermal data, to get the thermal data without dynamic position system.
Yeah.
But maybe it's possible. But a little bit risky, but maybe possible.
Yeah. Okay, thank you.
Other questions? Do you have other questions? Okay, so I would have one question related to your Kyoto University on-site laboratory, especially for students, if they are interested to join this kind of laboratory.
Yeah,
what are they supposed to do?
At this moment, Kyoto University side as well, we have no kind of budget enough to invite all students.
Oh, yes.
But if we have some of MOU based on the international collaborative research or international collaborative education system, we can get some more budget from Kyoto University. Of course, Kyoto University already have some more budget for the international student. This is also applicable. But
So-
we need MOU to use to apply that.
So are they supposed to join a certain project, research project in Kyoto University?
yeah.
Like subjects, for instance, like just to show their interest in that project?
Yeah.
To write something like a proposal, a short project?
Oh, yes, if we have if you're interested in the establish the new international collaborative research, especially with the disaster prevention research institute, this is my institute, that this is also applicable because now disaster prevention research institute announced the for the submitting the new project proposal about international research. If you access to the website of my institute, you can download, you can access the some of proposal and you can get budget to visit Japan.
Okay, thank you so much. If you don't have more questions, then we'll end this talk right here. And we'll invite you on Friday, because on Friday we have the students' presentation. Some of our students were, had the courage to present their work in front of Professor Ito today. So we are really happy to invite you all in Lavis. It will be at 10 o'clock, starting at 10 o'clock. We have a couple of presentations, the presentation and the short discussion after the presentation with Professor Ito. So please feel free to come and attend this reunion. And also feel free to contact him and talk to him. He's a very friendly. So, and he's eager to share his knowledge with us. So thank you very much for attending and
Thank you.